Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Joanna Smart from Business Review, and I will be your host. It's our pleasure to have Kamo with us today, who will be discussing improving product quality and time to market by optimizing time-dependent process modeling using multivariate analysis. Today's guest speakers are Dr. Frank Westad, Chief Scientific Officer, and Marie Pettersson, Marketing Director. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin this session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We will allocate some time at the end of the session to address any questions or thoughts that you may have. If you click on the survey widget, there are a few questions in there for you to answer in order to provide feedback. You can do this during or immediately after the webinar. Please use the yellow help widget if you require any assistance, and you can move, resize and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Marie.
Hello everyone, my name is Marie Pettersson. I am the Marketing Director of Kamo Software. I just wanted to give you a brief introduction of our company. We're based out of Oslo in Norway, and we go back all the way to 1984, where the first version of our unscrambler software was launched in the market. And this is really the core of our business, to do data analysis and modeling. With time, we have evolved, and we are now offering process applications such as Process Pulse, and also the Unscrambler engine, which are both tools to do online monitoring. And constantly we are innovating in this space. And for today, we're going to talk about batch modeling, which is primarily interesting for some of our key focus areas in pharmaceutical, biotechnology, in the chemical industry, food and feed, and more. And in our team, I'm really pleased to have a number of really knowledgeable scientists. And one of our long-time members of the Kamo team is Dr. Frank Westad. He is our scientific officer and also based out of Oslo in Norway. And he will be conducting the session today. So I'll hand over the controls to Frank.
Thank you so much, Marie, and hello everyone, and thanks for attending. So I'll go straight to the topic of interest here, and will be a short background, some words about the multivariate world, and data analysis structure for batch data, some of the challenges, and then our approach, and some example cases, and short conclusion. So just to give an introduction for an application that everyone can understand, but it's not really relevant for you in daily work, but assume that we want to heat water to 100 degrees C, and we're in different places in the world, and so it means that the water temperature will be different, and the question is, how can we then model this process, although we started different sort of starting points, which is not uncommon also in chemical reactions or in fermentation. So let's say now first we just plot the observations here as sample number, and we see that we start here at different temperatures, and in Norway, if we start with snow, of course, it will be a typical curve like we see here on the bottom blue. And then it's important to notice that this is not sort of time as such in the process of heating water. It's sort of the sample number. And we can always make these curves similar by using some time warping, but the question is if that then also after this procedure really describes the relative change in the process up to boiling water. So if you just look at how it progresses, which I just stole this from the internet, And then if we start in Norway, we see we start here and we have the blue curve. And then if we add then how it looks in New Jersey inside 20 degrees, it looks like this. And if you are 27 degrees, it looks like this. And then the 5 degrees starting point looks like this. So then what we really can do is now to show this in relative time. And we see that the common starting point actually is then 35 degrees. And the common endpoint is 100. This is maybe a special case because if you follow like a chemical reaction, it's not that they always ended at also in the same state in the chemical reaction, but here is no variation in the end point, which can be the case in other applications. So after this short introduction, I think we will do a quick poll. What application areas do you see when it comes to modeling and monitoring batch?
Hi there. Thank you very much, Frank. I'm afraid I'm experiencing a bit of a technical difficulty. Would you like to do the poll? Take over to do the poll?
Yes, I can do that. So we have the 4 application areas. Will be fermentation, chemical reaction, and then different unit operation in pharma industry like drying, or if it's some other also application you foresee.
Okay. If we go to the answers now. So the question was, what areas are of interest for batch modeling and monitoring? And the answers were fermentation, chemical reactions, unit operations in pharma or biopharma, for example, drying, or other. If you could just submit your answer, and now the results. So what do you think of those results, Frank?
Yeah, it's interesting that there is a majority of unit operations in pharma industry, biopharma, and I guess drying is a typical one. And also chemical reactions, which we see also interest in our approach to follow reaction that may last everything from half an hour up to 1 or 2 days. So I think it's as expected.
Brilliant, that's great.
So, yeah, thanks for that input. So now just a brief background. All this is known to most of you. Important thing is that we will accommodate changes in raw material, things we cannot control, other circumstances, and typically we can follow individual variables with control charts, with upper and lower limits, and look at what's happening over time for the batch processing. But we also know that looking at individual variables is not enough. So if you have a case here with 2 variables and we have the upper and lower control limits, then if we use the individual limits to say that the process is under control, we see that that space is too wide when there is a correlation between the variables. So we don't detect the outlier then to the right in that small figure. And that's why we use the multivariate methods, because then we still keep the same level of test, like the 5% confidence interval, although we have many variables. And then of course the PAT has been buzzword for many years, especially for pharma industry, and we need to use multivariate methods to analyze all the data from the different sensors we have, individual sensors, multi-channel sensors, and so on. And also, it's important before we do any modeling to look at what variables do we have in the system, in the process. For example, for fermentation, or if we dry something, which variables are controlled, because those are the variables we want to monitor, like within a normal sort of sweet spot, because they don't change over time. Then we observe variables that may change over time, like could be the moisture in the outlet airflow. It could be accumulated product, pH, glucose level, things like that. And also there is something maybe we didn't measure because we didn't have the instruments available, and something we don't know, which is also interesting in sort of looking for innovation. But all this will be going into the process or the system, and then we have a source of variation, and we need to also evaluate the models across these error sources to look at the stability towards, for example, raw material, batch lot numbers, and so on. And then we can then model the state of the process. Sometimes we make quantitative models. That's typical use also for models with the unscrambler to predict something, or we follow things over time in a more qualitative fashion. And then we come to sort of the multivariate tools that we have. Of course, the design of experiments, it's very important in everything we do in science. And we have different types of designs. We have the sort of standard ones to the factorial designs, and then often we also go after the first sort of screening to optimization, and also in most industries actually things are mixed to 100%. So mixture designs are often sort of more the rule than the exception in the businesses we are talking about here, and also to combine them with the process variables for the optimization. Then we come to the analysis of one data table, where we can look for relationships between the variables. Can we look if there are groups in our samples? Do we have outliers? And after that, we will go typically to say, okay, now we use methods to maybe to classify something, or say now we want to identify raw materials based on some instruments we have available, or we can discriminate between different states of a system. One typical application is to identify a counterfeit, for example, tablets, where we use various methods to define what is the normal situation, but also then for monitoring processes. Then we go to the quantitative models, where we want to predict something like inline without waiting for some physical samples to be sent to the lab for reference analysis. And this is also a typical use of our software, the unscrambler, to predict like the content of the active ingredient in a tablet, or moisture content, or another then sort of important properties of the product. So I know that some of you are already familiar with one of these methods for analyzing one table, principal component analysis, and there is in a nutshell. So the idea is to reduce the dimensionality by finding the underlying structures, and it's done by maximizing the variance in the data. And if we have only two variables, of course, we can display as a scatter plot. For 3D, we can display also in a scatter plot. But when we come to more than three variables, it's not that easy to visualize in the raw data. So then that's why we use PCA to summarize everything. And the application areas will typically be to explore the data. We can also see if we have redundancy among variables. Maybe we do some development in lab scale, pilot scale, and we see that, well, maybe we don't need all those sensors in the production line if we have the redundancy. On the other hand, redundancy is also good to detect if one sensor is failing. So we should have some kind of redundancy, I think, also in the production line. And also we use it for process monitoring, of course, in the multivariate SPC tradition. And another thing, also it's very useful to use then the PCA to analyze results from design of experiments if you have many responses. And we can visualize directly the effect of the design factors and their interactions. So the aim is to model the data into what is the structured part and what is the error part, and here also validation is very important. When do we say that, well, there is no more in this data set, we should stop, otherwise we are modeling noise, which we don't want. So here is an example. We have a chemical reaction, we have 3 historical batches, 3 variables, reactant, intermediate, product, and in this case actually they are predicted with a model based on spectroscopy. And then we can do PCA on the batches and follow the batch over time. And now if I just look at the raw data, because we have 3 variables, so that's one way to display it. We see, of course, the progression here over time, starting in the upper part, ending in the lower right in this case. So then if we do PCA on this data, what we get is the best 2-dimensional window in this 3-dimensional space. So the results will be typically visualized in 2 main plots. It's a map of the samples, and here we see, as I said, the best 2-dimensional window. In this case, we explain 99% of the variance, because here, of course, the sum of the 3 will be 100, and there is no other interferent variation, so we expect this to be a 2-dimensional data set. And also then we can see in the corresponding correlation loading plot, which we use quite a lot, because then also we see directly the explained variance, and the outer circle is 100, the inner is 50%. So now we can also see here that we start with a lot of the reactant, and then we have the intermediate, and we end with the product. So everything makes sense. So let me now just go to batch processes. And we know that the modeling is important for development and also understanding the process. And then some questions could be, well, how can I analyze the batch data if I have some design experiments I want to optimize the process? And also can I find the reason why the product quality for some batches lies outside specifications, or how can I visualize if there are effects from raw materials or season operator equipment? Because we want our models to be valid across different production sites and equipment. But then as the models are mostly empirical, we cannot say that it's universally valid, like if we have a first principle model that we believe is describing the process to a high degree. And then we can use the monitoring phase to look for out of control cases, like detecting events that we didn't expect. So now if we look at typical data from a process where we have only the samples and variables, it will be 2D, but in this case we have time as a 3D. In a 3D data cube, and that is the starting point for the model. So when we look at the data, we can also do a direct 3-way analysis. That's possible. We can unfold what is said the time-wise, so every row will be one batch, and then we have all the combinations of time points and variables as the columns. And we can unfold so that we have the rows being for all batches the different samples. And there are some various strategies how to analyze the data, but I recall that here if you look at the time-wise, and if the batches don't have the same number of samples, you cannot directly put them in one specific column in the data. So there is a challenge there. So the phases will be to analyze all the data, interpret the structure of the variables, maybe take out some outliers, create a model of what we call the golden batch sheet. It means that the end product quality is inside the specs. And then we store that model. We can also then sort of use the model offline, but the online is even of more interest. So we follow the batch over time and detect in real time out-of-spec situations, and then from that we need to take some action, maybe feed this back into a control system. So here is then a very simple example from this first dataset actually, where the number of samples is very different, like from the blue to the red. So if we display it like this, it looks like the three runs are quite different. And also another case is that if you have processes with the various phases, then there might be different lag times, and so it's not that easy to display the data just from the sample number, what is going on in a chemical or biological sense. You can also make, if you're not interested in following a batch directly from start to stop, you can also make a sort of a simple model of the end state. So we just take some batches and we make a model where everything has come to like the correct moisture content. So this is sort of a simple version where we don't care about what's going on here, but we know that we're inside. Just a second, there might be a technical problem.
Okay, we're just checking here. Can you hear us? Okay, so Frank, please continue.
Yeah, it seems we are online. So then just to go into the details of the unequal batch lengths. So two of those approaches, they require that it's the same number of points of time, but that's not always the case. Actually, the real data we're looking at, that has never been the case. And also that it starts in the same sort of chemical biological state, and also that it evolves in the same way to reach the end point. And also, if you want to model the data where we have the rows as batches and time points, to be able to estimate sort of the critical limits there dynamically, we also need the same number of samples. So we can always normalize the batches to length 1, or you can make variables, so say that this is like 1 to n will be in the maturity, but if things are non-linear and also don't follow the same pattern, it's not that easy to establish a good model with that approach. So what we think is the solution is simply to model the process in relative time. So it means it's independent of actually the process time as such, and also it's independent of the sampling rate. So for example, for that small example with boiling water, if in Sydney the temperature was observed every like 10 seconds and in New Jersey every 5 seconds, that doesn't really matter for our approach, because it's always in relative time from start to end. And also, once we have established relative time, we can show the individual variables in relative time, which is also quite an interesting concept. So we can show this to our colleagues that don't know about these methods, and they really don't need to care. They only need to know that how the things progresses in relative time for individual variables. So what we do is that we make a PCA, and here is one other example, a chemical reaction with 4 batches. So we make a PCA and we have the map of the samples here to the upper left. And we see that things are highly nonlinear here. So it's very easy to say that this sample number 1 to end will tell us what's going on from start to end. So the starting point is the lower left. And also we need to validate this model across batch. That's what we're interested in, the between batch variance here. So what we do with our methodology is to estimate the trajectory and the confidence intervals, typically shown with 2 or 3 standard deviations. And now we are ready to monitor a new batch. And here also it is shown, if you show one of these variables here, like the pressure in this case, it looks like the batches are different because the number of data points was not the same. But if we show in relative time, we see that it follows more or less the same pattern, although there is something special with batch number 4, which we in light blue, which we saw also in the score space, but still we have the relative time, which we can follow independently of the length of the batch or the sampling rate. So then in the real time, we will show the model with limits, and then we have various sort of statistical criteria to tell if something is not as you expect. We have the distance to that trajectory. We have the distance to sort of the model in terms of the residual. Is there something that we have observed that doesn't follow the pattern that we expect? And also we can drill down and tell which variables are the ones that have changed if something happened. And then we feed it back, and we don't do the controlling ourselves, but it can be fed back in real time over OPC or something to your control system. So monitoring a new batch looks like this. We just start to project a new batch into this score space, which is in relative time, and we see here that it starts actually outside, but it means that the reaction hasn't come that far as when we made the model. But still then after some time it will follow, although there is something here out of bounds for some time period of time. But then we can see which of the variables that have changed relative to the trajectory itself. So it's a dynamic limit. We cannot just use the mean of the model for the limit. So back to that first case with the chemical reaction, and now we can put on the limits here for that model. And now we can also here we can look at the reactant, and we can show just the raw data consecutive for the 3 batches or folded. And again we see that it looks like they are quite different. But if we show this in relative time, we see that the reason what the left-hand plot indicates that something is different is that we have much fewer observations, like from the batch in red and also the green than the blue. But we know that in the score space we see that they are actually following the same trajectory. And also we can show the so-called scores in this manner. So we can summarize sort of the information by using the scores and not the individual variables, if that's also something we want to display. And again we see that the sample number, it looks to be different, but in chemical time everything is fine, and we can put also the confidence limits on this this score vector. And also I mentioned that we can also visualize the distance not only in the 2D space but also as a dynamic limit in 1D, and this is what we do here, and we can use these for looking at finding outliers. And also we have the F residuals. It means is there something new? Is the pattern for the variables different than we expect? Then we see it in this plot. And also here we see that things might also actually go back and forth. It could be because there is a sampling issue, or maybe the reactions sort of stopped for some time. But still, we always just show it in relative time. So now we can project a new batch onto this model. And here we see it progresses, starting in the upper left and then in right. But also see that actually it's sort of reversing after it comes to the end. So it should have been stopped earlier. And we can also display it now in relative time or sample number. And we see a sample number, see that there is no progress from point number 55, which will be in the right-hand plot, will always be around 100% relative time. It means that nothing really happens, and it's time to stop. And then if we show the trajectory model distance, we will see immediately that we have sort of reached the end of the reaction, and it's time to stop. And then after that, we are sort of outside the boundaries. So this was with 3 variables. Let's go to a case with 6 variables. So this is a fluid bed dryer, and we have the typical variables: the airflow, inlet air temperature, product temperature, exhaust air temperature, inlet air temperature, and exhaust air humidity. So this should be outlet air temperature, by the way. So now we can estimate the trajectory on these batches. And in this case, once it is displayed here for me, we see first the map of the variables in this process. So we see the inlet air temperature is on the left side, and the exhaust temperature on the right. It means that they are negatively correlated. We see also product temperature here, inlet air humidity. So it makes sense. And we have the airflow describing the second dimension. And if you now add sort of the score plot here to look at the limits, we see the start and the end and the trajectory with in this plot. And if you put them in one slide, we see directly what's going on, and it starts up here, and then it will go through higher airflow in the lower part, and then it ends with high temperature in the exhaust air and also in the product. And of course, then the humidity, the inlet air, will also will be here in related to these 2 variables. So it makes sense. So this was 6 variables. What if we have 1093? Well, the principle is the same. So here we have also a fluid bed dryer operation, but we use some inline spectroscopy. And we do PCA on those batches, and we can project a new batch. So here we have the model for the 3 batches, and we see that we don't have a common start point as such, because the moisture content is different between the batches. So we start in the lower right, but after some time they will all reach like 7% moisture, where they start to follow by trajectory. And also it looks like one of the batches was sort of was stopped before it was dried, as the green and the blue one. And also we can analyze the data, and we can see that we're actually using the moisture peak, and this is then specific to those who know spectroscopy, that we have the signal for OH, which in this case will be moisture in this part of the spectrum. And also, although we have 1093 variables, the model has only 2 underlying dimensions, so we have a lot of redundancy, and we can also make a model with a limited number of variables if we like, but we can also keep all, and we can see if there is something happening in other parts of the spectrum that we didn't expect. So now we have established the model with the trajectory and the limits, and it looks like this. And then again, if we show like the the score for the first principal component, just as line plot, it looks like they're quite different. But in relative time, we see that they follow the same pattern to the right. Again, because the number of samples is not the same. And also we can show exactly the variable that we are sort of interested in, the moisture peak at one specific wavelength, then reflecting the moisture content more or less directly. So although many of the sensors, like spectroscopy, they don't measure exactly what we're after, we know from theory that we can still show quite many detailed sort of chemical information because we know where we expected signal. So again, we see that sample number is not giving us the right visualization of what's going on. In relative time, everything is fine. And also here, when we monitor a new batch, it was so that the sensor was failing for some period of time, so there was no signal. But then that doesn't really affect the relative time as such in the process. So when the sensor is back up here, we see now, in the meantime, we have come from like 11 to 8% moisture, and then we follow the normal trajectory, more or less CDN. We are slightly outside, but maybe it's still inside the spec as such. But then we can click on one point and we can see which variables that have changed. So this to summarize, we model the batch progression in relative time, so there is no need to force the batches to a common length, which will not be the correct way anyhow. And also we don't need to warp the individual variables to make them similar. And also we don't need to introduce what we call the maturity index, because the relative time gives the maturity directly, independent if the model is, or the data show non-linear pattern or not. And also we can summarize for the operators what is going on if you're inside the confidence intervals with just a line plot of the distance to the trajectory or the residual distance to the model. So then we come to how can we use this in real time, and then once the models have been established with our software, the unscrambler, it can be used online in Process Pulse. And here we see some of the typical applications. And then we store the models, and then we collect the data real time here on the left. And then we can monitor this with critical limits and display to the user directly.
So this is Marie Peterson again here, and thank you, Frank, for the great run through of the new methodology here. I also, in this picture that you can see right now, it shows you a good summary of actually everything that Frank talked about in one slide. But just to describe this a little bit further in terms of what kind of ways of using it there are. So starting from the top, it's really the unscrambler where you do the modeling itself, and then you can add the batch modeling plugin as a feature in that modeling tool. So what you also can do is add, as Frank mentioned, to the batch modeling and the unscrambler, you would take those models and put them into real-time play with a process pulse. You can actually use it in a real process monitoring scenario. And finally, at the bottom, I just want to mention if we have any instrument vendors, what we do for instruments is that we can implement this into the instrument directly and actually achieve the same thing. In other words, putting the model into real-time play. So that moves us to the Q&A session. So Joe, do you want to jump in and help us with the Q&A?
Great. Thank you very much, Frank and Marie. That was brilliant. So just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. So we've got a few here. The first one is, are there any limitations in number of variables or other limitations to consider?
No, not really. There is no limitation except maybe for the sampling rate. If you want to measure 20,000 variables every second, maybe there is limitation, but as such, like reading 1,500 or 15,000 variables from a spectrometer is no problem.
Okay, brilliant. The next question is, what kind of expertise do you need to operate with this approach?
Well, for the model building part, of course, you need to know the basis of the protocol analysis and interpretation and how to validate the models. For the operators, you might actually have several configurations running in parallel, and one for the operators could be that they see only like the two plots where they know that we are inside spec, everything is fine, and the experienced user can then show all the details and follow this more closely, and you can get a notification if something is wrong, and you can log onto the system and you can sort of get a warning if something seems to go out of spec.
Okay, brilliant. So the next question is, what does it take to implement this new approach to batch modeling?
Well, for the offline analysis, you will need the batch plugin in our software, the Unscrambler. And then once the models are sort of established, they can be saved as individual files, and then they are loaded into the model library in our online software process pools, or used with the engines inside, like an instrument vendor's software. And then you need to connect to the data source one way or the other. But that can be done via OPC link or reading ASCII files, or in the case of instrumental data directly from the file format. So it's quite versatile also from database or like a Pi database. It can be read directly in real time.
Okay, brilliant. Just another reminder for the audience, if you want to ask any questions at all, you can send them in via the questions widget at the top left-hand corner of your screen and click submit. So the next question we've got is, where, in what applications, does this new approach provide the biggest advantages?
Well, for the data sets we have analyzed yet, like 10-12 data sets, typically it has been, as I mentioned, the fluid bed operations, chemical reactions with the reactions will last everything, so anything from maybe 17 to 24 hours, and it's not always easy to find out why, because one will think that the raw materials are similar. And also fermentation is one case where we see that the bacteria, sort of, some will directly start and sort of progress in the different phases, and some might not. But in all those three kinds of applications, when we show relative time, we can still compare the different runs, and also in real time. So if the bacteria for one case will actually not start to grow, it means that the relative time just stays put, which is not the case if you show like the sample number as such.
Okay, brilliant. The next question we've got is, how have you validated this model in system to guarantee data integrity?
Well, the models are validated conservatively across the batch, so it means that if you have 10 batches, or batches with different raw materials, you will validate by taking out all the batches with one raw material batch, and then see if the other half then follows the same trajectory. So because it's not sufficient just to take the randomly 10% of the data points in the table. So it's important to know what validation level will reflect your sort of future use of the model. Is it across instrument or raw material, or what are the sort of uncontrolled sources of variation that you have in your system?
Brilliant. So the next question we've got is, has this approach to batch modeling been tested with FDA submission, and if so, what were the challenges you faced?
Right. Yeah, as you know, this approach is rather new, so I'm not aware of anybody sort of filing this for FDA, but the software itself is following like the CFR 21 standards. So any results from using the models will be no problem when it comes to audit. There's an audit trail in everything that is done, but I'm not aware that anybody has filed any application yet, because this is rather new, only like 3-4 months since it was available as a product.
Okay, great. Just another reminder to the audience, if you want to ask any questions, just send them in via the questions widget at the top left-hand corner of your screen and click submit. So the next question we've got is, what is the minimum number of parameters to make an MV model?
To make a model to monitor in real time, I guess was the question. Well, it's an interesting thing, but if you have only one variable, of course, there is no way you can find what is the relative time. But actually, with just 2 variables, you can always estimate a second component in the PCA model. It might not be having any information, but as soon as you have that 2-dimensional plot which tells you the chemistry or biology, you can actually use also this approach with just 2 variables. And the one variable might also be like a noisy one without information, but you still have then the relative time, and you can monitor with 2 variables as well.
Okay, that's great. Thank you very much for answering those questions. That's all we've got time for today. Any unanswered questions will be forwarded on to Marie and Frank, and they will answer those at a later time. Before we finish the webinar today, is there anything that you would like to say, Marie and Frank?
Well, thanks again for your attention, and I wish you all the best for your ongoing product development or process monitoring, and may your models be with you.
Brilliant. Thank you very much. So that just leaves me to thank Frank and Marie for what was a great presentation, and to thank Kamo for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. Once this webinar ends, today's survey will appear in its place, and we would appreciate it if you answer the questions in there. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a lovely day.